Hello, this is Mr. McMurray, and we're here on this bright, well, not so bright, still dark outside, but this wonderful Thursday morning, and aren't we all excited to be here? I'm sure. Okay, we're going to talk about chemical changes. Phew. Been a rough morning already. What can I say? All right, so we're going to talk about some chemical changes. We talked about solutions and stuff last time, and we just started, I think, getting to chemical changes. So, chemical changes. The only time we call them chemical changes, first of all, is when we are talking about physical and chemical changes. The rest of the time, we don't call them chemical changes. We call them chemical reactions because we have chemicals that react with each other. Okay? And the key thing about a chemical change opposed to a physical change is that a chemical change changes the chemicals that an object is made out of. Okay? So it's actually different chemicals than what you had before. Okay? And so it's completely different. All right. Now, say we have a piece of paper, for example, and I tear it into smaller pieces. Okay? Now, that would be an example of a physical change. I've changed the size, shape, and whatever of the paper, but it's still paper. It's still paper towel. It's still got the same characteristics that it did before. Okay? It's still exactly the same chemicals. Now, I can't completely put it back, although I could tape it or whatever, and it would almost be back. And generally, physical changes are easier to kind of undo, okay? But on the other hand, if I take a match, all right, and I take a piece of the paper towel and I light it, now, wow, let me put it out there real quick. All right, now I have completely changed it. I have smoke coming off of it. Okay, I have ashes that were not there before, still floating around here. Okay, I have ashes. I don't know if you can see that. Yep, on my finger again. All right, I had smoke. I had water vapor coming off. I had carbon dioxide, carbon monoxide, a whole bunch of other things. All right, and so basically, I can't put this chemical back together. Okay, I could take the ashes, put it in the ground, and water it, and eventually grow a tree and maybe make a new paper towel. But for the most part, these are completely new chemicals, and it'd be very difficult to re-put it back together again. All right, and so that is a chemical reaction or a chemical change because we've got completely different chemicals than what we had before. All right, now, therefore, you have the chemicals before and the chemicals after. Okay, and so in this case, the chemical before would be the paper towel. And those are called the reactants. They're the chemicals we start with. Technically, we also had oxygen in the air, which was necessary to make this reaction happen. Okay, so the paper towel and the oxygen would be our reactants, the chemicals before. They're called reactants because they react with each other. In this case, in the presence of heat from the match. Okay, and they react and make new chemicals. So the chemicals before are called the reactants. The chemicals after are called the products because they are produced or made by the reaction. So the reactants react and they produce the products. The products, in this case with the paper towel, would be the carbon or the ashes left here, also some minerals, okay? The smoke, carbon dioxide, carbon monoxide, water vapor, some other things that were in that smoke that came off. Those would be our products. All right? So that's just the before and after chemicals are the reactants and the products. Now, there are 5 main types of reactions, okay, that can happen. All right, we can either put chemicals together, we can take them apart, we can have chemicals trade partners, a couple different ways, or we can burn things, which is kind of a special case of taking things apart. We went from one piece of paper to all these other different chemicals that came from it. Okay, but combustion is kind of its own special deal, so we'll talk about that separate. But let's start with first synthesis. To synthesize something means to put things together. Okay, so if you put things together, you have 2 or more reactants, 2 or more different chemicals. You add them together to make a new chemical. Okay, for example, water. If we have oxygen gas, hydrogen gas, and we light it, it will blow up. But after it blows up, there will be water vapor formed. Okay, because if you put hydrogen and oxygen together, you make water. So you're taking 2 reactants, oxygen, hydrogen, both flammable, by the way, put them together to put water, which we use to put out fires. All right. Completely new chemical, completely new properties. Instead of being explosive, now it's actually puts out gas or explosions. Okay, An example of that would be also sodium, Na, and chlorine. It's also a good example of how you have different chemicals because sodium is a very explosive metal. We put it in water and it blew up. Okay, chlorine is a poisonous gas. Most of the mustard gas and chemical warfare gases, a lot of them have chlorine in it. It's a very green, nasty gas. Now you say, oh, but I got chlorine in my pool. Well, that's actually something chloride, okay, with something else added to it. Kind of like bleach is hypochlorite, sodium hypochlorite, okay? It's not actually just chlorine by itself. It's a compound, okay? We say you're adding chlorine, but technically you're adding a compound that has chlorine in it. All right, when you mix these together, we know the naming chemicals that NaCl is going to be sodium, IDE on the chlorine, so it's going to be chloride, sodium chloride, or table salt. So once again, an explosive metal that blows up when it touches water, green poisonous gas, put them together, you got table salt, totally different thing. So it's brand new chemicals, and so this would be synthesis. Sodium and chlorine would be our reactants, okay? So we have more than one reactant, something plus something, and it makes one product, just one chemical. Now, you could have 3 or 4 or 5, however many compound elements over here, but they all go together to make one compound or one product at the end. All right, that's synthesis, putting things together. Now, the opposite of synthesis would be to break things apart. Decomposition, when things break down, dead things break down on the side of the road, we say it breaks down. So in this case, you have one reactant, and it breaks down into several products, okay, or makes several different things. An example would be if you take water and if you stick a battery and you take the 2 wires from a battery and stick them underwater. Be careful, you don't want to electrocute yourself. Let's make sure this is just like a 1.5 volt or something. Okay, and you stick it in water, you'll notice that from each wire it starts to bubble up gases. At one wire will produce oxygen bubbles and the other wire will produce hydrogen bubbles. Okay, and what you're doing is you're separating water. You're going from H2O, breaking it down into hydrogen and oxygen gas. All right, now it's not balanced. Don't worry about that right now. But if you don't know what that means, then really don't worry about it. But at any rate, you're taking one chemical and you're breaking it down into 2 parts. Okay, so that is decomposition. You have one reactant. Everything on this side of the arrow before the reaction is the reactant. Everything on this side to the right side of the arrow is a product. Okay, so you have one reactant, several products, 2 or more. All right, single replacement. All right, this is when a metal trades places with the metal of a compound. Okay, so you have this element or metal element, and it takes the place of a metal that's already in a compound. It's kind of like if you went on a date with your best friend and his girlfriend, and you were the third wheel, so you got to go along. Okay, but halfway through the date decides she likes you better than she does your friend, and she goes home with you. Or if you're a girl, then the other way around. But whatever, you get the idea. And that's kind of what happens here. Okay, so we have a pair of chemicals, zinc and phosphate, so zinc phosphate, all right? But if you put copper there, guess what? The phosphate says, I'm more attracted to the copper than I am to the zinc, so it dumps the zinc and it jumps over here with the copper. Now we have copper phosphate and the zinc is all by itself, okay? It replaced or took the place, the copper took the place of the zinc, all right? And so this is called single replacement because one element is taking the place of another element. Now, technically, you could do it with this side too. You could have had maybe SO4 here, and maybe it took the place of the PO4, and so you end up with zinc sulfate instead of zinc phosphate. But either one, the metal or the nonmetal, trade places and say, hey, I would rather join up with the other one. All right, and it's called single replacement because it's in that. Now, double replacement is similar, except for now you have 2 couples, and they both trade. It's just like if you went on a date with your girlfriend and a double date with your friend with his girlfriend, and halfway through the date you decide, yeah, I like the other one better. And so y'all just swap dates, or the dates swap you, whichever, however you want to look at that. But anyhow, so, whoops, sorry about that, I got a little carried away there. But this would be like you have silver nitrate plus sodium chloride. Okay, this is AgNO3, silver nitrate. So silver is with the nitrate, sodium is with the chlorine. But when you put them together, the sodium says, hey, I think I would rather go over here with the nitrate, and the silver says, oh, that's okay, I'd rather be over here with the chlorine. So they just swap partners, and now we have, instead of silver nitrate, we have sodium nitrate, and instead of sodium chloride, we have silver chloride. Okay, and so they've just completely traded partners, and we have completely different chemicals than we did. But we start off with 2 reactants, we end up with 2 products, but they have swapped partners. All right, now the last one is combustion. In order to combust, you have to have oxygen. So burning basically always requires oxygen. Okay, and it's kind of like a special decomposition sometimes, but it's not exactly, because you always have to add oxygen. So we think, like the paper towel, oh, I started off with one thing, and then I end up with all these chemicals. But technically, you have the paper towel plus oxygen, which is always around in the air around us most of the time. Okay, in this case, this is methane. I believe that's natural gas. Okay, and if you light that in the presence of oxygen, it makes carbon dioxide and water. Okay, and if it burned perfectly like that, you would get no pollution from it. Unfortunately, it doesn't. You also end up with CO, which is carbon monoxide, and some other things. But if it burned perfectly, this is what you would end up with. Gas is a longer chemical than this, but if gas burned perfectly cleanly, it would only give off carbon dioxide and water vapor coming out the back end of your car. Unfortunately, once again, it doesn't do that, and so you end up with all the different kind of smoggy type things that come out of your car. All right, but anyway, you start off with methane, you add oxygen, and you end up with carbon dioxide and oxygen. So key thing is you add oxygen, and therefore it causes something to burn, and then you end up with usually water and usually carbon dioxide. All right, and that's basically it. Those are the 5 types. We'll talk more about those later. Otherwise, we're done for today. So have a great day, and we'll talk to you tomorrow.